Okay, so to finish up for the semester, I listed out the things that you have to turn in. And experiment 9, I made that available a little while ago. You guys did that. That was the last lab we performed. And what I was thinking is you can just upload that to your, directly to your Canvas. If you don't have a scanner, there's apps out there you can put on your phone where you can take a picture of it and it converts it to a PDF. I think the students at some of my other UC students and some of my students at C State use something called Genius Scan. You can Google that if you don't have the ability to scan that. But go ahead and upload that as a PDF to your Canvas. There's a link for that. I checked this morning. Well, actually, I checked a little while ago, and nobody. Hopefully, you guys are working through the Exam 3 project videos. So far, nobody submitted those yet. So that should be not gonna say an easy 100 points, but there's no reason why you shouldn't get 100 points on that. Don't wait till the last minute. Hopefully, you got to start on those. I think there's like 15 or 16 short videos. So go ahead and get that out the way. Also decided to put the first question of the exam, the final exam is up, and actually it'll be available. The link will unlock right after this class. I highly recommend that. You don't need to know, you don't need to review anything, just you want to get that out the way. And do a good job on that first question, because if you mess up other parts of the exam, I can weight this question a little bit heavier and help you out with some points. So make sure you take a look at that. And you don't want to, wait till the last minute and have to do exam 3, the question for exam 1, and the exam 4, and the rest of exam 4. So exam 4, I'm thinking it's going to have 10 questions on it. I was going to erase this because I might have maybe 10 to 15 questions on it, but one of them will be available right after class. So I will take a look at that at some point in the next day and go ahead and do a good job on that first question. And then all you have to worry about is the balance of it, exam 4. So that should be everything that you need to turn in. I do have a note here for exam 2. So exam 2, I shared with you the scores, and the scores were on your Canvas, but I shared with you the stats on it. I'm of course not able to go over the exam with you. If anybody needs or wants to see that, I'll be happy to. We got to figure out how. I might be able to do a virtual meeting or something. I don't know how to do it right now, but I put a question mark by that exam 2. I did have one person that said, "Hey, I like to, see what I did on there," and I'm fine with that. Just got to figure out a way to do it. I think that I got to check with human resources to see how this COVID thing works. I think once you test negative, I might be able to go back. I have to see what the rules are. We may be able to actually meet face to face if somebody's going to be around. I don't know if you guys are going to be around next week, so we'll work that out. So if you have any interest in seeing that, just let me know. Let me get all this grading and all that stuff done out the way, and then I'm gonna hold on to those exams. Now I decided what I'm going to do with I got a bunch of graded work I need to get back to you if you want it. You don't have to take it. What I'm going to do is early tomorrow morning, I'm going to sneak up to the campus. I'll have a box. I'm going to have all your stuff separated, and I'll put all the papers in the box. I'll put it over by the window in our classroom. And so if you want the papers, all the graded papers, if you want them, then you need to go in there. Try to do it Friday if you can, if you're going to be around on Friday. If you're not going to be here on Friday, let me know, and I won't put it in the box. I'll hold it back if you want it. But if you want your graded papers, then I'll put it in the box. I'll set it over by the window, and you guys can grab it. And I don't know if I want to go back up and get the box back if you don't get it. I don't know. I might just leave it there. But I'll have the stuff there if you want it. And I'll send out an announcement just to let you know it's available. If you don't want it, don't worry about it. Either I'll come back and get it, or the janitors will toss it. I think I have everything in the grade book, though, except for the couple assignments I had with no name on them. And then there's one more, the last CEAMP problem that you did for me, which I don't know if it was a homework or a quiz. I can't remember. But that's the only thing outstanding that I have that's not graded. So everything else should be up to date. I do have papers from other classes I'll go through just to make sure I didn't miss any Vides paper get anything, misfiled or something like that. But for the most part, what you see for your grade should be pretty accurate once I put the CE assignment in there. Exam 3 the project is designed to help your grade. So I know I have a few people that the scores are probably a little bit lower than what you might want, but just do a good job on exam 3 and question 1 for exam 4. And I think everybody should be okay as far as the course is concerned. So we can talk more about this after class. Let me go ahead and get through the material. We should finish early enough. I'll stay and see if we have any questions. And right at 3 o'clock, this question 1 for the final exam will become available. And then sometime tomorrow, the rest of the questions will become available. And like I said, don't hold me to the 2 to 10. It it'll be at least 10. It could be a few more. I don't know. I still have to write it. So let's get into the material. And then, as I said, if you want to, if we need to talk about something, since this is our last session, I will stay after and we can talk through the video. So before we get into the lecture, let me run something by you here. I think we talked about a circuit called the Wheatstone Bridge, but let me ask you, if let's say I have a light bulb, and I tell you at this point right here, there's 10 volts, and at this point right here, there's 10 volts. Let's say this is point A, and this is point B. Is there any way for me to get the light bulb to light up? Would that light bulb light up, yes or no? And anybody feel free to answer. Would the light bulb light up, yes or no? Nobody's responding. Okay, well, let me see who I can, let's see. How about Ryan? What do you think? Well, do you think the light bulb would light up if I have a circuit where I have 10 volts on the right, 10 volts on the left? Would that light bulb light up?
It shouldn't, since there's no voltage drop from the thing.
Yeah. It's impossible for it to light up because there's no voltage drop. There's no potential difference. There's got to be a difference of potential. If I lowered this down on the right, if I lowered that down to 9 volts or 8 volts, then I have a voltage drop of 1 volt or 2 volts, and current will flow from high potential to low potential. So in this situation, there's absolutely no way for the light bulb to light up. Well, let's think about this a different way. I'm going to get a voltage divider. We'll just call it VT. I'm going to hook up a voltage divider. And on my voltage divider, I'm going to make each resistor exactly the same ohmic value. So this is R, and this is R. And if I do that, if I make each resistor the same ohmic value, then what should happen is each resistor should get exactly half the total voltage. So this one right here is going to get the total voltage divided by 2 across it. And this one right here is going to get the total voltage divided by 2 across it. So they're going to get exactly half of VT. And now what I'm going to do is take another voltage divider and put it in parallel with the first one. And you guessed it, I'm going to give these exactly the same ohmic value resistors. And so this one's going to get the total voltage divided by 2 across it, and this one's going to get the same. All of these resistors, since they're all the same value, have the same voltage across them. So now I'm going to put a point A right here and a point B right here. And I'm going to take that same light bulb I just showed you a second ago. I'm going to put that light bulb in the middle of this thing and ask the question, the same question I asked before, will that light bulb light up? And the answer will be no. Why not? Well, for exactly the same reason it didn't light up before. I have the same voltage on the left side of the light bulb as I do on the right side of the light bulb. Therefore, there's no voltage drop across it. It cannot light up. It's impossible for that light bulb to light up. Now, we talked about this circuit in class briefly, I think. This is called a Wheatstone bridge. So if I wanted to, not only will the light bulb not light up, I can actually erase this light bulb, remove it, and I can put a piece of wire between points A and B. I can put a piece of wire between there, and absolutely no current will flow through the wire. Matter of fact, the circuit can't tell if that wire is there or not because of the fact that the voltages are exactly the same at point A and point B. So what you can do is you can think of, we can call this like a virtual wire. I'm going to show it as a dotted line. A virtual wire. Virtual. So it kind of, it's like a mechanical wire, but it doesn't have any current going through it. And this is just really just a concept, an idea, a mental construct, if you will. Okay, so remember this. File that in the back of your brain somewhere. And let's go back to the op amp. And I want to review the main point from the last discussion, and I want to give you some new information. So one of the main points that you want to remember is if I have an ideal op amp, what three things do I know? If it's a perfect op amp, I know the gain, and this gain was called AOL. It's called the open loop gain. I think I put that on the board. I don't know that I explained it, but I'll explain it today. But a perfect op amp is going to have a voltage gain of infinity. A perfect op amp is going to have an input impedance of infinity. And a perfect op amp is going to have an output impedance of 0. If a manufacturer could build the perfect device, this is how it would behave. Now, will they really have a voltage gain of infinity? Well, no, but it'll be really, really high. Will they really have a ZN of infinity? Well, no, but it'll be extremely high. Will they really have a Z out, an output impedance of 0? No, but you can expect the actual op amp to have an output impedance that's really, really low. So if I could build a perfect device, this is how it would behave. So manufacturers try to get as close to the ideal as possible, and they do a good job of that. So this is what we talked about in the last class. Now I want to give you what we call the op amp golden rule. So write this down. Golden rules. And there's 2 of them. There's 2 golden rules. The first golden rule is, for an op amp, no current flows into the input terminals. If I have a perfect op amp, this ideal op amp, no current will flow into the input terminals. The second rule is that the op amp will always try to, let's say op amp will do what it needs to do to keep input voltages the same. So if you understand these 2 rules, then it'll be really for you to understand why and how op amp circuits function the way they do. So golden rule number 1, no current flows into the inputs of the op amp. Golden rule number 2, the op amp will do whatever it needs to do to try to keep the input voltages the same. Now, let me show you a circuit. I don't have a lot of space here. This is called a inverting amplifier. And that inverting amplifier, circuit for that, what we're going to do is we're going to take the non-inverting input. And remember, the op-amp has two inputs because the front end of it is a differential amplifier. And we name one positive and one negative. That's not the polarity. This is the non-inverting input, and this is the inverting input. And so if I ground this, what's the meaning of ground? Well, it means that this is at 0 volts. And what I'm going to do is I'm going to put a resistor here, and I'll explain this in just a second. And then my voltage that I'm going to amplify connects to the inverting lead. I'm going to call this resistor R. This voltage on this, we'll call this V2. This is my V2 input, and we'll call this V1 input, V1. If I tie V2 to ground, then the voltage here at V2 is also going to be 0 volts. Well, why is it 0 volts? Well, one reason is, the easy way to think about it is because the golden rule says that the op-amp is going to do whatever it needs to do to keep both input voltages the same. So if you make this 0 volts by connecting it to ground, then this is going to be 0 volts too. It's going to do what it needs to do to make that 0 volts. Now in reality, is it really 0 volts? No, but it's so small, it's so close to each other, you can assume that it's 0. If you actually did this in the lab, you measure a slight voltage, maybe microvolts. But for all practical purposes, it would be 0. Well, is this a safe assumption that that voltage right there is 0? How do we know it's 0? Well, if I have an ideal op-amp, then I know that my voltage gain for ideal op-amp, my open loop voltage gain is going to be infinity, or my regular voltage gain, my voltage gain is going to be really high. I can at least say that. Now, how do we get the voltage gain? Well, that voltage gain is equal to, as you know from the CE amp, is equal to V out over V in. And in this case, my V in is this V1. And you can see from the formula that if this is my output voltage, my V out is here. If this value right here, if that's really high, if that's infinity, the only way for that to happen is that this one has to be really, really low, next to 0. So just from the voltage gain equation, you can see that pretty much has to be the case. So we can say because of that high voltage gain, that input is going to be really, really high. So either take it from the golden rule or take it from the math, you can kind of see that these two voltages here are pretty much the same. Because they're the same, because they're close to each other, this one is actually physically tied to ground. This is a mechanical ground. We can think of this other one, since they have the same, just like I showed you in the Wheatstone bridge, when you had the same voltage on the left and the right, you put a physical wire there, it doesn't really upset the circuit because there's no potential difference. You can actually think of this as being tied to this one. Since the voltages are the same, you can think of this as being tied to ground also. And in books, they call this a virtual ground. It's an actual thing that exists that you can read about in your textbooks. This idea of a virtual ground. Basically, it's not a mechanical ground. A virtual ground is a ground, or you can think of it as short to voltage, but no, it's an open to current. In an actual ground, current can actually flow to ground. In a virtual ground, it's like a short to voltage, but no current can flow through it because it's really an open circuit. The point is both of these voltages are pretty much pretty much the same. And so now let me erase this. I want to draw this bigger so I can explain this inverting amplifier. I just want you to see this idea of virtual ground because it's going to help with the explanation. But we got a problem. The problem is this voltage gain. I want to say a little bit more about that. The open loop voltage gain on an ideal device is really, really high. But just like the Q point for the BJT transistor, it's unstable. When we did that base bias, we know that the Q point was unstable because beta was unstable. Beta is unstable because beta varies with temperature. Beta varies with the manufacturing process. Beta varies with several things. So if any circuit calculation depending on beta is not a good thing when you're dealing with an amplifier. What's fine for a switch, but not for an amplifier because that beta would be all over the place. So what we did is we changed our base bias configuration, which is beta dependent. We moved that resistor from the base to the emitter. We call that emitter bias. And then we noticed when we did our analysis, we never ever referred to beta in them at all because that particular circuit was beta independent. Well, we have the same kind of issue with the op amp. The voltage gain for the op amp is called the open loop voltage gain. You'll know in just a second why they call it the open loop voltage gain. But that voltage gain, although it's really, really high, and we like that, the problem is it's unstable. The open loop voltage gain is very unstable. It can vary for a particular op amp like the 741. It can be as low as 20,000, which is still huge. It can be as high as 200,000. It can be all over the place. And so just like beta, what we like is a more stable quantity. We don't like quantities that change from device to device or with temperature and so forth. So how do we stabilize the voltage gain? To do that, we use something called feedback. Feedback. And I really do wish I had more time to go into it. Normally when I teach this course, I think I mentioned to you guys when we were face to face that a course like this used to be 2 semesters. You would first study electronic devices, which is pretty much what we spent this semester talking about. And then the next part of it would be integrated circuits, which is really what the op amp and the 555 what they are. But we'd have 2 semesters to do it. And when I talk like that, I could actually go into the details of feedback, what it is. I don't really have time to do it now. But let me just mention there's 2 types in electrical engineering. There's 2 types of feedback. There's positive feedback and there's negative feedback. And what are we feeding back? Well, we're feeding back some of the signal. We're feeding back an output signal to the input of some kind of device. And positive feedback, what that does is we use that when we want to make something oscillate. So it's for oscillation. Negative feedback, we use negative feedback, we want to stabilize something. So for example, the reason, we didn't go into the details of it, but the reason that emitter bias circuit, the reason it worked is because it actually had feedback, had negative feedback that locked that Q into place. So that's all I'm going to say about feedback. Well, we actually use this type of feedback for op amp circuits, not to stabilize the Q point, but to stabilize the voltage gain, because the voltage gain is all over the place. It's really high, but it's all over the place. So what we got to do is feed back some of the output signal back to the input. And if you want to know more about negative feedback, I mean, your book probably talks about it a little bit, or you guys can Google it or YouTube it. We just don't have time to go into it. So with that said, I'm going to show you our first circuit design. This is the non-inverting amplifier. I'm sorry, this is the inverting amplifier. We'll do the non-inverting next. This is the inverting amplifier. Okay, and I've already showed you part of the circuit. But let me show you the complete circuit. So we got our op amp. We have our leads, our inverting and our non-inverting leads. What I'm going to do is I'm going to tie that non-inverting lead to ground, which forces the input voltage here to be 0 volts because it's grounded. And then I'm going to drive this input. So we're using the inverting input, which means that if I send a signal into that input, and I'll get the amplified version of it, but it'll be inverted. So I'm gonna drive that input with current, but I'm gonna first go through this resistor. We'll just call this resistor R. And then here's the voltage I want to amplify. Okay? So what I gotta do now is, if I just use the circuit like that, and don't forget guys, I actually have the leads here. I'm not showing the power. Sometimes, you know, you got a VCC, and now here you got a minus VEE. So I'm not showing these leads just to keep the circuit simple, but they're really there. So here's my V out. What I'm going to do is I'm going to take a resistor. I'm actually going to tie the output to the input through this resistor. And this resistor is called a feedback resistor, RF. That's a feedback resistor. And this circuit I just connected up, we tied the output to one of the inputs. That's a feedback loop. This is a feedback loop. And so when I talked about the open loop voltage gain, AOL, that's the voltage gain of the device without this feedback loop. The loop is open. And the open loop voltage gain for any op-amp device is really, really, really high. The good thing is it's really high. The bad thing is it's unstable. And so what we like to do is we like to make this voltage gain more stable. And the way we do that is by using negative feedback. We take some of the output quantity and feed it back to the input. What we get is we get less voltage gain. So my voltage, this new voltage gain with this feedback loop is called the closed loop voltage gain. This is the way you want to use the op-amp. Never with this one, but with this one. The closed loop voltage gain is always way smaller than the open loop voltage gain. So you may say, okay, well, why would you want to do that? Well, what we gain by doing this, we get less voltage gain, but we get more stability. So this voltage gain, that closed loop voltage gain, once you add negative feedback to the op-amp circuit, then this voltage gain is stable. It will not vary at all. And so it's a trade-off. We trade some voltage gain for stability. And so this is the configuration, and one of the configurations that you will want to use the op-amp in. Closer. Remember what I said about question? Does someone have a question? Okay. Now remember what I said about, well, actually the golden rule, that the op-amp is going to do whatever it needs to do to keep both inputs the same. And so what that means is that if I tie this to ground, let's just call this, I think we call it V1. Then this input right here, V2, is also going to be 0 volts. We've already discussed the reason why. So you can think of this point right here as a virtual ground. It's not a physical ground or mechanical ground, but for all practical purposes, it acts like ground because both of these points have exactly the same voltage value, 0 volts. So if you look at this circuit long enough, you can actually divide the circuit into two circuits. Just make some room. You have, if you think about this point right here as being ground, you actually have an input circuit. Let me draw it to see if you can mentally, if you can see this. What you have is your VN, you have that resistor R, and then the other side, at this point, you got that virtual ground. Not a physical ground, but it acts like ground. So I'm going to show it not with a solid wire, but with a dotted wire. Most books will show virtual grounds with broken wire like that. And so you got that virtual ground, and that would be my input circuit. And then over here to the output, if you look at this, I got this output voltage, so I can actually draw that as another circuit. I got my V out, and V out connects that resistor, RF, so it goes through the resistor, RF, my feedback resistor. And the other side of it is also connected to that virtual ground. So I'm going to show a dotted line here for the virtual ground because it's not a physical ground, but it acts like a ground. And this will be my output circuit. Here's my output circuit. And here's the input circuit. So you can think about the input circuit as being like this and the output circuit as being like this. Two separate circuits because of that virtual ground. And then I want you to remember, I erased it, but remember that first golden rule. The first golden rule says that no current flows into the input of the op amp. Well, is that a fair assessment? Is it good to say that? Well, let's think about it. If you think about the ideal op amp, we know that the opposition looking in, the input impedance, in the perfect world is going to be infinity. In the not so perfect world, we know at least know it's going to be really, really hot. So if I have an infinite impedance looking into that input, if I have an infinite impedance, then I'm going to have zero current. I can't have any current where there's an infinite resistance or infinite impedance. So what that means is that the current that leaves this source, we'll call that current IN. This is the current into the circuit. That current is going to flow through the first resistor, but no current is going to go to that input of the op amp because the resistance is too high, the impedance is too high. So the current has no choice but to go through this circuit right here, through my feedback circuit. So that would be the path of that current. And I'm showing this because you can see clearly that that current has to flow through, that current IN has to flow through R. So in this circuit right here, the current that this resistor receives is going to be that current IN. And then when that current IN gets to that virtual ground, no current can go into the input of the op amp because the impedance is too high. That current actually has to go through the feedback resistor. So it's actually going, now notice the way this is drawn because my output voltage I'm showing right here, but that current is kind of like going the wrong way. It's actually going this way. So the current is actually going that way. That's my IN. So because of the path of IN, from the voltage source through my resistor, no current into the op amp inputs because the impedance is too high, that current is forced to go through the feedback resistor into my output circuit. And these two at the bottom are equivalent circuits. Well, hopefully if you follow that, then it doesn't take too much to see that this voltage, this input voltage, that input voltage has to be equal to the current through the resistor times the value of the resistor. That's just Ohm's law. So that current is going to equal Vn times R. And likewise, this current over here, again by Ohm's law, the output voltage is just going to equal the current times that resistance. It's going to equal IN times RF. And so just by using some simple logic and some Ohm's law stuff, we can come up with these equations. Now, why do we want these equations? Because if we think about voltage gain is equal to V out over Vn. But my V out is this. So my V out is IN times my feedback resistor and my VN is this, which is IN times my other resistor, and you can see what's going to happen. These currents are going to cancel out. So when I use this op amp like this, when I use this non-inverting op amp with that feedback loop, then my voltage gain can be calculated by just taking the feedback resistor divided by the other resistor. Now this voltage gain is not the open loop voltage gain. You only get that when you don't have the feedback circuit. We call this voltage gain the closed loop voltage gain. So I want you to write down, you want to remember, for a inverting amplifier, the voltage gain, the closed loop voltage gain is equal to the equation I'm showing you right here. I'm not giving you any calculations or practice to do. We'll do that on the final, but you'll need this equation. Now, normally when you see this equation, they'll put a minus sign in front of this just to show you that the voltage is inverted. I'm not going to do it here, but if you look in your book and you see a minus sign in front of it, that's where they get the minus sign to show you that the signal is inverted. That's not important for what we're talking about. So for a inverting amplifier, look how easy the voltage gain is to get. Now go back to the CE amp, or the other amps that we talked about, made from the BJT transistors. A lot more complicated. Here, this is pretty beautiful, elegant, and simple. The other thing about this is, if I'm looking into here's my eyeball, if I'm looking into the amplifier circuit like that, because of this virtual ground, I'm actually just looking in this circuit right here. And I'm seeing this resistor as the input resistance, input impedance. So also for this amplifier, something else that's nice is that ZN stage, or that ZN, is going to pretty much, we'll say, is equivalent to R. Now you might say, well, hold on a second, I thought the ZN was infinity. Well, yeah, that's when you don't have the feedback loop. So these are all closed loop values, and these are the equations that you'll need to work problems for the inverting amplifier. So that's pretty much it. Equations, I could have just gave you the equations. They're pretty simple. I mean, there's not a lot there. But why are these equations the way they are? That was the purpose of this discussion. So, does anybody have any questions on how the inverting amp works, or just on the inverting amp in general? Any questions on the op amp inverting amplifier, or comments? Let me pause and see. Okay, pretty easy. It's not a lot here. Let me show you the other configuration. This is the inverting amplifier. The inverting amplifier. When I want to look at the non-inverting amplifier, it's another basic amplifier circuit. Now I'm showing you these basic circuits, but you can combine these and build these to be more complex circuits and to do other many things. Op amp has so many uses. I think we mentioned that before. So I'm just showing you the basics of the basic here, and these are the two basic circuits. So this would be my inverting amplifier. So let's talk about the non-inverting amplifier. So this time we're going to inject a signal into the non-inverting lead. It's going to look like this. This time what we're going to do is we're going to actually have a voltage divider over here. This is how we're going to get our negative feedback. So here's a voltage divider. We'll call this R2, R1. And I'm going to inject a signal into the non-inverting lead. here's my VN. And then I'm going to take the inverting lead and I'm going to tie it to this voltage divider. So now this is my feedback loop for this circuit configuration. I get my negative feedback from this voltage divider. And basically what's going to happen is that whatever the voltage drop is across this resistor, that voltage drop, that's going to be the input voltage to my amplifier. Why? Well, if you go back to the golden rule of op-amp, it says that the op-amp is going to do whatever it needs to do to keep these voltages the same. So if this is VN, then it's going to want this voltage right here to be VN. But also because we're using the fraction of this voltage divider, we're feeding that to the input of the op-amp. So we're going to call that VN. No current can flow into the input of the op-amp. Why? Well, we say that the impedance is too high. And so basically, the current that flows out of here, it has to actually flow down through these two resistors like that. So that's going to be my I. I'm just going to call it I. And I've already mentioned the fact that this voltage divider is feeding the input of my op-amp, that VN is across R1. So I can write an easy equation for that, that VN is going to equal this voltage divider current, I times R1. And my output voltage is output voltage across both resistors. So my V out, to calculate that, it's going to be that same voltage divider current, I, is going to be times both resistors, R1 plus R2. C is a series combination of those two resistors. And so we can get our closed loop voltage gain, ACL, like before. It's always equal to V out over VN. But V out is equal to this. V out is equal to I times R1 plus R2. I think there's some glare up there. Hopefully you guys can see this. And my VN is going to equal this. It's going to be I times R1. And so, like before, my I's are going to cancel out. And now look at what I got left, which is going to define my closed loop voltage gain for this amp. It says that the closed loop voltage gain for a non-inverting amplifier is equal to R1 plus R2 over R1. And then we usually rewrite this. This is going to be R1 over R plus R2 over R1. And R1 over R1 is 1. So once you do the math, you combine everything, you end up with 1 plus R2 over R1 for this circuit. This will be my closed loop voltage gain. And again, this is a very, very, very basic op-amp circuit. But if you're going to calculate voltage gain, then that's what you would do. You use that formula. So you got choices with this, and these are pretty much, I mean, we went through the calculation with the CE amp and the CC amp, but I think most people are not going to build discrete component amplifiers like that. You would use you probably would use something like an op amp if you use a small amp, maybe for like a M3 3-player, whatever you call it, your cell phone. If you had a big audio amp, you need something else. But for small amplifiers, the op amps are great. Now I do want to show you one more thing here. Does anybody have any questions over this non-inverting circuit? Okay, well let me show you one more thing that hopefully from the discussion of the golden rules you can understand. sometimes what they'll do is they'll take this circuit right here. And we said that the voltage gain, closed loop voltage gain was 1 plus R2 over R1. Well, sometimes you'll see this circuit, and what they'll do is they will eliminate these resistors right here. They'll eliminate the resistor, and they'll tie the output directly to this input terminal. And the question is, if you do that, what effect would that have on the circuit? Well, basically what you've done is you set this right here. You set that to 0. And if you set that to 0, then the voltage gain, my closed loop voltage gain, is going to equal 1. Why would I want that? What the heck is the purpose of a voltage gain of 1? Anybody? What might this do for me? This would be a good This would be a good question for the final. Where else did we come across a voltage gain of 1? I can't believe out of the 12 people, nobody remembers where we come up with a voltage gain of 1 was the what?
It was with the cascading amplifier, so that way you kept the Z in for the first one high instead of it being a low one for a load.
That's correct. So that what we did, we cascaded a CE amp, which has a lot of gain, but the gain is dependent on the load. So when you connect a low value load like an 8 ohm speaker, then that voltage gain from the CE is gonna depreciate. It's gonna drop. We call that overloading the amplifier. How do we fix that? We cascaded that with a CC amp. It's also called an emitter follower. Why? Because the emitter follower basically had a voltage gain of 1, but it had a high input impedance. We wanted the voltage gain of 1 because in this case we weren't concerned about amplification. The CE amp does that for us. We need a high input impedance and a low output impedance, so the high input impedance allowed us not to disturb our output circuit of our CE amp to lower the gain, and the low output impedance allows us to connect to a low impedance load like a speaker. We have exactly the same situation here. By removing the feedback resistors and just tying the output of this non-inverting amp to the input, and what you get is you get a gain of 1. So this amplifier doesn't amplify. The amplifier does not amplify. But remember what we said about the input. The input right here, ideally is infinity, but we at least know that the input, looking in here, is going to be really, really, really high. Because an ideal op-amp is going to have a high input impedance. And looking in this way, the output impedance is going to be really, really, really low, which means it can drive a low impedance load like a speaker. And so basically this could be equivalent to our emitter follower. I think in books and other circuits, they call this a buffer. A buffer circuit. This is a very, very, very common buffer. They use op-amps for this all the time. So why would you want to do this? Well, let's say you have some kind of sensitive instrumentation or sensitive circuitry that you want to connect something else to. You need a high input impedance, and when you connect it up to say this is the sensitive circuitry right here, if you try to connect a low impedance load directly with that, it's gonna affect the circuit. You can put a high impedance load, you can use this buffer, and it looks like a high impedance load looking in this way, and you can use that to drive a low impedance load, just like the emitter follower from the CE amp cascade that we talked about. So this is another very common circuit. So what I've shown you today was, number one, we looked at the inverting amplifier. And from that, we introduced this concept of virtual ground. And if and when you read your book, you'll probably mention virtual ground, or whoever YouTube video you look at, they'll probably try to talk about virtual ground. It's kind of hard to explain, so I try to do my best for you to visualize how that virtual ground works. So we looked at the inverting amp and introduced a virtual ground, and now you know the difference between the open loop gain and the closed loop gain. Open loop gain is the gain of the device with no feedback. Closed loop gain is the gain with feedback. We want the gain with feedback because that gain, although it's lower than the open loop gain, it is very controllable. It's stable. And then we looked at the non-inverting amp. So you got choices. You can have an inverting amplifier or non-inverting amplifier, whichever one. And then a special case of the non-inverting amp is when I remove the feedback resistors and now have a buffer amplifier. This allows me to interface a high impedance with a low impedance and not disturb the circuit. So this is pretty much all. I'm not going to do any analysis with this because, I mean, really just got these voltage gain formulas. There's not a whole lot there. It's just multiplying and dividing. But we did talk about some concepts that I might ask about. So I'll leave the analysis for you on the exam, but the concepts, hopefully this cleared up these op-amp circuits. And so really this kind of ends the lecture. I don't have anything else to say about this. Does anybody have any questions for me about any of the amplifier circuits that we talked about today? Okay, well, a couple things. This is recorded. If anybody needs to see this lecture over again, send me a text and I'll post this to YouTube and you can rewatch it if you need to. Now, right at 3 o'clock today, your Canvas is set up so that the first question on the final exam will become active or available. And so again, I recommend you don't have to do it like right away, but go on and get that out of the way. And like I said, it may not be weighted evenly. Like normally all my test questions are weighted evenly, but I'm gonna have a little leeway on there in case you mess up another part of the exam. I can look back at that first question and I can maybe pull credit out of that. So it's very important that you do a good job on that question one of the exam. And what I would recommend is if you got some downtime today or tomorrow, go ahead and get that question out of the way. You don't need to look anything up. You just read it and then you'll answer the question. The rest of the exam will be due, the final exam will be due sometime tomorrow. I'm sorry, not due, it'll be available sometime, probably won't be first thing in the morning, but it'll be earlier in the morning, and it'll be available all the way through Monday. I can't remember the time, the shut-off time, but it'll definitely through Monday. So over the weekend, try to get it out of the way. It shouldn't be a big deal, but it will take a little bit of time. So don't wait till the last minute to try to do it. Definitely try to look at it and get it out of the way before Monday, I would say, if you can. And then the other thing that I mentioned was I'll be putting your work up at the school tomorrow in a box, cardboard box by the window in our classroom. So anything you want, it'll be all separated. Just find your name, take your stuff out. And if you look through that material and you have questions over, my grading or anything you might have, just let me know. Send me a text, keep the document. Anything with a check mark on it, I pretty much grade it for completion. I mean, obviously at this stage, I'm not going to go through every single problem, but if you look like you were doing things right, if I checked it off, it was graded for completion. If that's an actual grade on it, then that means I went through and actually looked at your numbers and calculated and all of that. So I think everybody should be in good shape. I don't think there's anything else. Just remember when things are due, you got your experiment 19 that needs to be turned in as soon as you can. You have the other exam stuff that I just talked about. And I don't think there's anything else, but if there is, just send me a text and remind me. I did have one person ask about turning in work. Pretty much everything. I think you guys have turned in everything weekly. You should be pretty much up to date. If there's one or two things that you missed, let me know that you missed handing in, and I can probably take it. But I'm not going to go all the way back to like week one and take, if you missed stuff earlier in the semester, I'm not going to go back and regrade that stuff. I already went through it. So if you missed something like in the last couple of weeks, maybe you didn't turn in the CEM assignment, or I know a lot of people didn't turn in that battery assignment, which I was surprised. I don't know if you forgot or not, but like that I'll take. If you didn't turn in the barrier assignment, that was meant to be a free 100 points to help your quiz grades out. So if you look on your grade, you see, well, hey, I didn't got a 0 for the barrier assignment. You probably half the class didn't turn that one in. So something like that I'll take, but I don't want to go all the way back to week 1 and start grading stuff because you just didn't get it into me. So I think that's pretty much all I have to say. Anything else, you can send me a text. Now, a couple of you guys have been texting me, but I haven't responded because I'm getting texts from you guys, from Cincinnati State, and then dealing with a bunch of other stuff. But now that this grading is pretty much out the way, I'll be able to better respond to your texts, either tonight or tomorrow, something like that. So I think that's it for me. I'm going to stick around. Does anybody have any questions or comments for me while you have me online? And if you don't, we can always talk through text, so you can give me a phone call or whatever. Anybody have any questions or comments?
I have a question.
Mm-hmm.
One of the I think it was lab 7. I turned it in, but I think maybe I didn't put my name on it, so I got a 0 on that.
Okay, I don't think I'll look through. I'll look. I think I graded everything but it may be 1 or 2 papers out there that I didn't grade. I'll look for that. And I think I remember you being. I don't think you missed any labs, did you?
Yeah, I turned in all the labs. That's why I was.
Well, I mean, as far as your attendance, I don't think you missed.
Yeah,
anything.
I didn't miss any labs.
Now I did. There were a couple people who. Some people, I forget who it was. I think I had 2 people that had missing assignments, but the assignments were stuck in another assignment. Like you put it inside of somebody stuck something inside of the research. Remember the research you guys did on the optoelectronics? I found 2 assignments stuck together in there, So if I went through, I'll go through and see if I see it, but we'll work it out, whatever it is. And guys, let's say you're at and I'm not saying that I'll look for your work if you want me to, but if you're at let's say you're at like a 85 and you're missing a quiz or one thing like that, is not going to make you jump up a whole letter grade. It might give you half a point or something like that. So where that becomes important is, let's say you're at a 89.9 or 89.5, you need that extra thing. Hey, I'm missing something. That's going to be important. But if you're like kind of in the middle of a grade, it's not going to move you up a whole grade point or something like that. But I will look for it and I'll see, and just contact me maybe Sunday and see if I see or find your paper. Okay. I think I pretty much keep everything together. So if you turn it in, I should have it somewhere.
All right, thank you.
So okay, now you said that was experiment what now?
7.
Okay. And does anybody else have a question?
Hi. I turned in the battery assignment. I got a 0 on the grade book, but I think I turned it in, the battery assignment.
I think I went through all of those. Here's what I'll do, guys. I kept your stuff separate from my other classes, so I don't think I got any papers mixed up with theirs, but I'll go through, because pretty much what I have is pretty much what you see as far as what I have. So if you got a 0, then I don't think I have your paper, but to be 100% sure, I'll look through my other papers just to make sure that they didn't get out of sequence or something and maybe be mixed in with another class. So we'll see.
Okay.
So that is, let me now that one I can always send you another copy. That won't take you long to do it all. So if you didn't turn it in, or we're not going to freak out about a grade for the barrier assignment, because that's a real easy assignment to do. If we don't find it, at least you can go ahead and redo it. So that's not a big deal. But I did write your name down, and I will look for the barrier assignment for you. Anybody else?
Yeah.
What was sorry, go ahead.
On the battery assignment, if we didn't turn it in, when can we turn it in?
I think what I want you to do is you probably can just email that to me. I'm not gonna I don't know. Maybe I should just make an upload link for it. I'll make an upload link for it, and you can upload it. You can scan it, or you can use that that Genius app and take a picture of it.
Uh-huh.
Or you may even be able to do that. You might be, if your cell phone is, you have a good cell phone, you can snap a picture of it, and I can see it clearly. I can grade it right off the picture. You can do that. That might be the easiest thing.
All right, that sounds good.
So if you do that, just say, take a picture of it, say battery assignment, and then give me a day, maybe about a day. If you don't hear from me in the day, then send me another text and say, hey, I sent you the picture. And what's my grade? Just to remind me, because I'm doing a whole lot right now, as you can imagine.
Okay, thank you, sir.
Okay, and Mr. Clark, before you leave, are you there?
Yes, sir.
Yeah, I have something I want to give you, so I just want to make sure. I know the semester is ending. Maybe after the exam is over and everything, I'll shoot you a text. And I think you say you live in Cincinnati. I just got something I want to hand you. So let's talk after the semester is over, maybe next week sometime. Shoot me a text, or I'll shoot you a text, and I'll meet you somewhere.
All right. Thank you, sir.
Okay. Now, so who else had a question?
What was that battery assignment? Because I tried looking for it, see if I had it, and I couldn't find it. I was trying to remember what it was.
This one we talked about amp hour rating. Life of a battery is amp hours over current drawn. There were 2 graphs that I handed out. There was pictures of batteries, and we talked about life of a battery. And with that was another paper with 6 problems on it called the amp hour. It was an amp hour battery assignment, I think it was the title. So it has 6 problems on it, and it's titled battery assignment. What I'll do is I'll post that to your Canvas, and you guys can see what it looks like. And if you don't have a grade for it, I mean, I'll look for it, but I'm pretty sure I went through most of the stuff for your class. But I'll look for it, and if you hadn't turned it in, like I said, it's not a big deal. I'll put it up on Canvas, download it, work the problem, send it out. And you can just take a picture of it with your cell phone and send it to me, and I'll give you a grade for it. Pretty much people get an A or a B on it, and if you just do the work, you'll get a good grade on it. So I'll put that up, and I'll send out an announcement when I posted that. I think I got it on my desktop at work, but I might have a copy of it here, but I'll make sure it gets up on the Canvas. Okay, and I think go ahead.
Just to confirm, you said how we can send you a late assignment directly by the message, taking a picture, or sending an email to you?
The battery assignment?
No, I have labs.
Oh, the lab, you have more than one lab? The only lab you should have should be Experiment 19. Is there something else that you have?
Yeah, I have like 3 more that I didn't turn in.
I think what you need to do then is, are you able to scan those or not?
Yeah, I'm able to scan them.
Scan them and then send them to me by email. But you just want to, when you do that, you want to send me a text and say, hey, I emailed you. At this point, I'm getting a lot of emails from a lot of different places, so it's easy for me to miss an email. So go ahead and scan them, put them all together in one email, send me the email, and then follow the email with the text, so I'll know that you emailed me and I know to look for it.
Okay, thank you.
And the rest of you guys can do the same thing. You can, if you didn't turn, especially a lab, you want to make sure you get all those turned in. The only thing I won't accept is I'm not gonna like take homework 1 or homework 2. I'm not going all the way back to the beginning of the semester, but I can be lenient or flexible with the labs and the battery assignment, that kind of stuff. I don't mind. Anybody else?
Yes, there was 1 week that I missed because I was out of town, and I think I turned in a couple assignments all at once that were late because I missed them, and I have zeros for those. I'm not sure if you maybe missed those.
If you turn them in all together, separate from everybody else, then I might have those. Who is this? Is this Owen?
Yeah, this is Owen.
Okay, let me write your name down. So do you remember how many assignments you might have turned in?
Maybe like 3 or 4.
Okay, let me see what I have with your name on it, and I'll get back with you over the weekend. Send me a text over the weekend, and I'll go through. Pretty much I got all my UC stuff graded, but I do have a bunch of papers from the other school, and some of that stuff, I may have 1 or 2 things in that in that box with those papers. So give me a chance to look through those papers, and I'll see if I have anything for you, and we'll see. If you turn it in, I have it, so that shouldn't be an issue. But as long as
Okay.
you turned it in, then it shouldn't be a problem.
Okay. And then you said for like any other late assignments for like what Clark brought up, should we like title the email anything so that you like make sure you see it and stuff?
I think what you want to do is just make sure anything you're going to submit is all in one email.
Okay.
And then, yeah, just make sure you put put me at something in the subject heading like missing work or late work or whatever you want to name it. But the important thing is that you text me to let me know that you emailed me.
Okay.
Where I get confused, guys, is because I have stuff going up on Canvas, I have stuff going up on Blackboard. Some students will email me stuff that they should have, and it gets really confusing for me. So as long as I can get stuff in one place, I think it's okay. So if you email me something that should have been turned in or uploaded, just make sure it's all in one email so I don't have to look for it, and make sure you send me a text so I know to expect it from you. And if I'm here working, as soon as you text me, I'll go grab it and download and put it where it needs to be. Anybody else have a question? Okay, if anyone else has a question or concern, you can text me. I won't be able to respond right away. I do have another class here shortly that I have to prep for, but just keep me posted or keep watching your grades, and we'll get everything taken care of and done. And guys, I really enjoyed the class. Hope I see you guys around, and we'll keep in touch. So I will talk to you guys later.